This demo video will start by giving a brief introduction to the MySQL cluster product. After that, we'll view a live demo of MySQL cluster in our labs. In the demo, we'll see node failures, cluster upgrades and reconfigurations, and all the while there'll be a real application running and you'll be able to see that that application is uninterrupted throughout all those operations. The internet continues to grow at a rapid rate and all aspects of it are huge. Data volumes, numbers of subscribers and revenues. It should come as no surprise that data volumes are growing at a much faster rate than anyone previously predicted. McKinsey Global Institute estimates this growth at 40% per annum. Increasing internet penetration rates, social networking, high-speed wireless broadband connecting smarter mobile devices, and increasing machine-to-machine interactions are just some of the technologies fueling this growth. Global e-commerce revenues are expected to reach $1 trillion by 2014. The growth in the volume and importance of internet services puts extra demands on the database, which is critical to driving those services. The web is interactive and so needs to be able to massively scale out write capacity in addition to reads. Users expect everything immediately and so real-time performance is important. Businesses rely on their web services and cannot function without them, and so 99.999% availability is needed in more and more places, not just telcos these days. This means avoiding outages when there are faults, but also for planned maintenance activities and schema changes. Innovation is key for businesses. The database should enable rather than get in the way. For example, you can download and start developing on MySQL cluster without buying anything. And then licenses or subscriptions are inexpensive if you want formal support. The database needed to support such a massive growth in data have to rise to meet new challenges, including scaling write operations, not just reads, across commodity hardware, querying and presenting data at ultra-low latencies to deliver a real-time user experience, 24/7 availability for continuous service uptime, and reducing barriers to entry, enabling developers to quickly launch new innovative services. Of course, you can argue that databases have had these requirements for years, and that is true, but they have never had to address all of these requirements at once. For example, some databases have been optimized for low latency and high availability, but they don't have a means to scale write operations and can be very difficult to use. Other databases may be very simple to start with, but lack capabilities that make them suitable for applications with demanding uptime demands. It is also important to recognize that not all data is created equal. It is not catastrophic to lose pieces of log data or status updates. The value of this data is more in its aggregate analysis than in individual elements. But some data is critical, such as e-commerce transactions, financial trades, customer updates, billing operations, order placement and processing, access and authorization, service entitlements, etc. MySQL Cluster delivers the characteristics demanded by today's applications, without having to give up on the important benefits of relational databases, ACID transactions, SQL for queries, etc. Services generating and consuming this data still need the data store to meet the challenges discussed above. It is necessary to protect data integrity with ACID compliance, run complex queries against the data, while leveraging the proven benefits of industry standards and skill sets to reduce cost and complexity, all while scaling write operations with high availability and real-time responsiveness. These are the four core design goals of MySQL Cluster. ACID-compliant relational database, with SQL and NoSQL interfaces. Write scalable in real time. It's a distributed auto-sharding multi-master optimized within memory data structures. 5 nines availability. It's got a shared nothing, integrated clustering and sub-second recovery, local and geographic replication, and online operations. And finally, low barriers to entry. It's open source with multiple APIs, management tools, and all running on commodity hardware. MySQL Cluster has been deployed extensively across both telecoms and web workloads. These workloads are characterized by demands for high write scalability, real-time responsiveness, and extreme availability. Cluster first proved itself in telecom subscriber databases embedded into HLR and HSS, Home Location Register, Home Subscriber Server. These are truly mission-critical applications. If they go down, no one can place or receive calls on a cellular network. We have one customer who has embedded Cluster into their HLR HSS products used by carriers around the world, collectively serving nearly 500 million subscribers per day, platforms and value-added services over converged IP networks. enabling telcos to offset declining voice revenues. Over the past 18 months, we've seen very rapid adoption of Cluster for web workloads, as these start to demand the same levels of availability and performance of telecom apps. Typical workloads include managing user profiles, session management, e-commerce, etc. This picture shows the architecture for MySQL Cluster. In the second half of the picture, we've got the data nodes. These are the machines or processes that actually store and act on the data. Sitting above that, you've got the various API nodes. Starting on the left-hand side with the C++ NDB API, which is the fastest native way of getting at the data, and on the right-hand side you've got MySQL servers, and it's these MySQL servers that provide the SQL access to the data. Sitting between those, we have various other NoSQL methods of getting to the data, with memcached, Java through ClusterJ, a REST API, and also LDAP. It's important to note that none of those API nodes actually store the data. The data is all stored down in the data nodes, partitioned between different nodes, where any change is written synchronously to two different places, so one data node can fail, and you can have sub-second failover to the other. Completely transparent to the application. There's a great deal of fault tolerance built into this architecture, and on this diagram we can see all of the processes or nodes that could fail, while the database would still be able to give full access to the data, reading and writing from any row from any table. Before demonstrating some of the high availability features of MySQL Cluster, I just want to show you how simple it can be to create your first cluster running on a single host using MySQL Cluster Manager, which is one of the commercial add-ons for MySQL Cluster. This is available from MySQL Cluster Manager 1.1.2 onwards. So a single command, mcmd -- bootstrap, and it goes on to create a full cluster, albeit running on a single host. Here we see the configuration that's going to be used for the demo. There are two applications running at the top of the screen. The first, noted by the red pen, is writing screen draw coordinates to the database. The second is reading and displaying those coordinates. These are represented by the red lines moving in the display window. By viewing the display window, you'll see that the database continues to both read and write data from the applications while it is upgraded, reconfigured, etc. The MySQL cluster data nodes, shown at the bottom of the screen, are where the data is physically stored and managed. The data nodes are also responsible for other core functions including replication, failover, and recovery. The MySQL cluster application nodes, in the middle, provide the interface from the applications to the data nodes. In this example, we'll be using MySQL Server, which provides an SQL interface for the application. We could alternatively use the direct APIs to directly connect the application to the data nodes, bypassing SQL altogether. These include Java, C++, LDAP, and HTTP interfaces. The final nodes are for management. We show one here, but for best practice you would deploy two nodes. The management nodes are responsible for configuration of the cluster and for handling network partitions, i.e. avoiding split brain. In this example we show that the application keeps running even as one of the VAR data nodes fails unexpectedly. Because we synchronously replicate data between data nodes and all nodes are active on a shared nothing architecture, failover is sub-second and the application keeps running. When the failed data node recovers, it is able to rejoin and resynchronize with the cluster without any recovery needed at the application level and without the need for the administrator to do anything. This demo shows that when one of the MySQL servers stops, the cluster remains operational, reading and writing data. You'll see that the drawing application keeps on running. If the user connects via the JDBC driver to connect to J, then failover from the application is automatic. Otherwise, they would use something like a load balancer to fail over the application to other MySQL servers. Here we also show that MySQL Cluster is a multi-master database, so the application can write to any of the MySQL servers and updates are instantly available through all of the other MySQL servers. This gives high throughput when you have many concurrent operations on the database without needing to implement data sharding in the application. We can reconfigure the cluster without any application downtime. This demo specifically shows the effect when we change a configuration parameter applicable to all of the data nodes, in this case failure handling. The change is applied and each data node process is restarted in turn without affecting the application. In this case the change is applied and the nodes restarted automatically by MySQL Cluster Manager, the round console window at the foot of the screen. MySQL Cluster Manager is a commercial add-on to the MySQL Cluster, available to licensed users of Carrier Grade Edition. Note that you could also make this configuration change without MySQL Cluster Manager. It would just take longer and need more manual intervention. We can upgrade the cluster without any application downtime. This demo specifically shows that the new version is installed first to the management node and then to each of the data and application nodes in turn. A rolling restart is initiated to apply the upgrade, but the application remains operational. In this case, the upgrade is applied and the node is restarted automatically by MySQL Cluster Manager. Again, you can perform the upgrade without using MySQL Cluster Manager, but there'll be a lot more typing and a lot more scope for error by the user. You can observe that the version changes from 7.1.4b to 7.15 as each node is restarted. We can scale MySQL Cluster online by adding new nodes with no application downtime. Great when handling rapidly growing user transaction or data volumes. The demo specifically shows that 2 new data nodes are added, but MySQL servers can also be added dynamically. The configuration files are updated on the management server, which then pushes them out to the existing data and application nodes, which run a rolling restart to recognize the new resource. The data node processes are then started on the new servers. Again, we have automated via MCM, but this can be done manually as well. To complete the online scaling, data is repartitioned automatically across the cluster, again with no downtime. Repartitioning is performed so that data from existing tables can be split amongst all data nodes in the cluster, freeing up space for new data on the existing nodes. After repartitioning, the new nodes are able to fully participate in the cluster, providing additional compute and storage resources. Here we can see how the schema can be extended with no impact to the application. Behind the scenes, we've got an NDB-enabled application that is constantly adding tuples to a table. In the top window here, we see a process constantly counting the number of tuples and also displaying a single row. In the bottom half, we're making schema changes, adding columns to the table, and you'll see that in the top window, the application just keeps on running. In this example, we show MySQL cluster application and data nodes being monitored by the MySQL Enterprise Monitor. This enables us to ensure that any issues that could affect application performance or availability are detected quickly before they become a problem. Here we are specifically monitoring data node memory use and MySQL Server CPU utilization and connections. This is new functionality in MySQL Enterprise Monitor 2.3. Here 2 data nodes are down and Mem detects this, sending an alert to the administrator. The administrator can click into the detail and will receive recommended actions. We could configure this as an email alert or an SNMP trap for forwarding to a ticketing system or other type of management framework. By following this link, you can learn more about MySQL Cluster, including white papers, webinars, data sheets, and case studies.